Hey guys, welcome to my little study room here. I promised you I was going to make a little video to kind of supplement what I had talked about in class because we have an exam coming up and I don't want to make you wait all the way until Tuesday to really get this last little bit down. Most of this is just going to be examples that are going to actually kind of help you with the homework. So I'm going to try to keep this short. It's just about the curvature. We talked about it in class, and what we had noticed in class was that if we have the position function in terms of the arc length s, then there's a nice formula for the curvature, right? We just take two derivatives of that position function with respect to s. These are derivatives with respect to s here. And then we just take the norm of that. But more commonly, we will be given the position vector in terms of t. And what we might hope to do is, well, what we could do, of course, is convert it. So convert, and we did this in class, from t to s. So we could take our position function in terms of t, write down what the arc length s is in terms of t, and then use that to replace our function so that we have a position function in terms of s. Right. So, but the question might come up, could you come up with a curvature formula that directly comes from the r of t side so that you don't have to go through this conversion and proceed that way? Turns out that there is such a formula. Let me just kind of show it to you here briefly, and then I'll do an example of it. Okay? So the curvature, remember that by definition, it's just the rate of change of the unit tangent vector with respect to s. We take the norm of that, right? I can think of that as the norm of, I'm going to write it this way, dt ds, okay? Which, if I want, I can then replace that with sort of a larger quotient. I can take the tangent vector, differentiate it with respect to time, and then I can take s and differentiate it with respect to time. Okay? So what you're getting out of this then is, well, t prime of t. So see, now I've brought the time back into the equation. And the norm of, well, ds dt isn't a vector, it's just a scalar function. But what its value is, if you remember, it is literally just the speed of the object. So actually, this is a perfectly good formula for the curvature, that it has everything expressed in terms of t. And we can use it to find the curvature without having to go through the intermediate step of finding the arc length. Okay, so let me just put this formula up here for the time being, and then we're going to use it right now. And I'm just going to show you an example. Okay? So we have this quotient right here. All right, so this is the curvature formula. The nice thing about the video, if I'm erasing something that you need to look at again, you can just rewind me or pause me or whatever and go back at any point. So that's kind of helpful. Let's try this example here. I just took this one out of the exercises from the book. So I'm going to let r of t equal the vector t, comma, sine of t. So this is literally just the graph of the sine of x, basically. Okay, y is equal to the sine of x, because x is the same as t. And we want to find the curvature. So let's find the k value. All right. So it makes sense to take the derivative of the position function here. So I'm going to do that first. I'm going to find r prime of t. Very easy, just slot by slot derivatives, yeah? 1 and cosine of t. Oh, I forgot to mention, I have a particular time in mind. So find the curvature at t equals pi over 2. This is the question right here. Find the curvature at time pi over 2. So here's my velocity vector. I need to find the speed, so that's just the norm of this vector. That would be the square root of 1 plus the cosine squared of t. And that's on the bottom of this curvature formula that I just derived for you a minute ago. Okay? Now let's talk about the numerator. I'm going to have to start by finding the tangent vector. Remember that the tangent vector is just the ratio of these two things. It's just this ratio right here. So it's just literally going to be, well, I'll write it this way. 1 over the square root of 1 plus cosine squared of t times the vector 1, comma, cosine of t. That's the tangent vector. And I'm going to need to take the derivative of it. All right, this is, remember I told you this can be messy. So what you would do here with this is use the product rule on it. Use the product rule. So I could take the, maybe it would be better to write this as a negative 1/2 power. Let me just take the derivative of the first part here first. So negative 1/2, 1 plus the cosine squared of t to the minus 3/2, and then times the derivative of the inside function, which would be negative 2 cosine of t sine of t. So all of that is just the derivative of the first part. I'm going to multiply it by the second part. Alrighty. And then I'm going to add the first part times the derivative of the second part. So it's a little bit messy. The derivative of the second part would just be 0 and negative sine of t. Alright. So we get something that looks kind of like that. And what we are going to do, though, is we're going to actually, we can plug in our time now. Okay, we've taken all of the derivatives that we need. We can plug in our time, which is pi over 2. And the amazing thing, of course, is that the cosine of pi over 2 is 0. That means that this scalar in front here is actually 0. So this whole entire part of our expression goes away. Cosine of pi over 2 is 0 here as well, so we just have a 1. This is just 0, comma, negative 1. All right? So t prime of pi over 2 is just 0, negative 1. So clearly its norm, when we plug it into the curvature formula, the norm of that, I'll just go ahead and put the pi over 2 in here. I'm going to have to divide by the norm of r prime of pi over 2. But the beautiful thing is the norm of this vector is just 1. And if I put pi over 2 in here, I also get a 1. So the curvature at this particular time is exactly 1. So it isn't so bad. Okay? Now, so that's using this formula. It turns out there's another formula for the curvature. I'm just going to give it to you right now. This is not something that is obvious, but it's a formula that I think is worth knowing because it can make things even easier. It's basically, it is a formula for the curvature. So here's another formula. And this one doesn't even use the tangent vector. Okay, so this is really very, very nice. What we can do is use this formula here. Again, we have a fraction. What we do is we take the norm of the cross product of the first and second derivatives of the position vector. Basically, it's the velocity crossed with the acceleration. You take the norm of that, and then you divide by the velocity, basically it's the speed, cubed. Okay? So this one is not obvious where the formula is coming from, but as you can see, it makes our life even easier now. We don't have to use the tangent vector like we did in the last example. So if we use this formula, right, things get even a little bit more straightforward. So for example, find the curvature, find k, for r of t equals t squared and t cubed over 4 at the point 2, 4, 2. Okay? Find the curvature along this curve at that particular point. By the way, you might notice if you compare the position vector with the point, you'll see that the time that we're talking about is actually t equals 2. If you plug in 2 for t, you get exactly this point right here. So what we would do for this is we would just take the first two derivatives of this, right, in order to be able to use this formula. to use the formula, I have to take the first two derivatives. The first derivative is just 1, 2t, and 3t squared over 4. And then the second derivative is 0, 2, and 3t over 2. Easy to take those derivatives. And we're going to plug in t equals 2 into these. So what are we going to get? If I plug in 2, I'll get 1 and 4 and 3 for the first vector. And I'll get 0 and 2 and 3 for the second vector. All right? Now I need to cross those together. So r prime cross r double prime. We have I, j, and k. And I'm just going to put the first vector, 1, 4, 3. Second vector is 0, 2, 3. And I start working this out. I get 12 minus 6. I get negative 3. And I get 2. I'm going kind of fast, but again, you certainly can pause me and stop if there's any questions as we're going along here. Okay, so that's the cross product vector. Is that what I got? Yeah, okay. That looks fine. Okay, so there's your cross product vector. The norm of that is, well, it's going to be the square root of 36 plus 9 plus 4. Now that would be the square root of 49, which is just 7. Okay, so the numbers come out real nice on that. And I have to divide that by, in this formula right here, I have to divide that by the norm of r prime of t cubed. Well, the norm of this is the square root of 1 plus 16 plus 9, which is the square root of 26. Okay, square root of 26 right here. And so for my final answer, I'll just put it right here. I've got 7 over the square root of 26 cubed. So in other words, 26 to the 3/2 power. All right? Pretty easy to calculate that using this formula. Okay? Lastly, one last thing. In the case where, what if you just had a curve? What if you just had a curve, y equals f of x? And you wanted to know the curvature of it. Of course, you can think of the position vector for that as just being t, f of t, and 0, right? You could just literally use this, and you can write down a formula for the curvature by just applying this formula. If you just apply this formula, right, what you're going to get, the norm of the derivative of this, okay, let's just kind of derive it here. 1 and f prime of t and 0. If I take the norm of that, I'll get what? The square root of 1 plus f prime squared. Square root of 1 squared plus f prime squared plus 0 squared. And the square root of all that. And then I have to cube that, right? So in other words, it's actually, let me write it a little differently here. It's just going to be the 3/2 power. It's a square root, but then we have to cube it. Okay? And then on the top, if you take the cross product of this, okay, if you take the cross product of this function, so let's just see here, I, j, k. Well, actually, I'm sorry, we have to find the r double prime. Got to find the r double prime. We're going to get 0 f double prime of t and 0 here. So if I put in 1 f prime and 0 and f double prime and 0, I got a lot of zeros there. When I do my cross product here, I'm just going to get f double prime in the first slot. I'm going to get f double prime here. I'm going to get 0 in the middle, and I'm going to get, for the k slot, I get 0 in the first slot. Sorry. The I component is 0. The j component is 0. The k component is f double prime. What's the norm of that vector? Well, it's literally just the absolute value of f double prime. So here's a curvature formula that applies to a function in the xy plane. Let me do an example of that now. And then you'll have all the examples that you need, okay? So here's an example. Find k at x equals 1 for y equals 2x plus 4 over x. Okay? So this gets remarkably simple, okay? This is my f of x right here. Okay, so I'll just point out here, f prime, the derivative would be what? 2 minus 4 over x squared. And f double prime, take another derivative, would just be 8 over x cubed. Both of these are going to be evaluated at 1. When I plug in 1, I'll get negative 2 for the first derivative, and I'll get 8 for the second derivative. Let me come over here to finish the calculation now. We're doing this at x equals 1. So if I take the second derivative, which was 8, I'll put it right there. And then on the bottom, I'm going to take the f prime and square it. So negative 2 squared is 4. Add 1 to that, I get 5 to the 3/2 power. There's the answer. Okay. So the point being, we have several formulas for the curvature. We can simply take the magnitude of the derivative of the tangent vector with respect to s, or we can take the magnitude of the derivative vector of the tangent vector with respect to t, but then I have to divide it by r prime of t, or I can take the cross product, the cross product of r prime of t with r double prime of t, and divide it by the cube of the norm of the first derivative. Or in the case when we actually have a function in the xy plane, it's just the absolute value of the second derivative of the function divided by 1 plus the first derivative squared, all to the 3/2 power. A bunch of different formulas to use. This one is great if your position vector